You are waking up in total absolute darkness. The air around you is incredibly heavy, thick with this sharp scent of salt, decaying leaves, and ancient, damp earth.
Yeah, that really rich, heavy marsh smell.
Exactly. And you are entirely enclosed in a subterranean tunnel just waiting in the pitch black. Suddenly, you feel it.
Just a tiny shift.
Right. A subtle, almost imperceptible shift in the atmospheric pressure pressing against your body. It is a silent, invisible signal that the ocean, which has been churning violently just inches above your roof for the last 6 hours, has finally retreated.
Meaning it's time.
It is time. You reach up and push against a sticky, airtight plug of mud that has sealed you in. As it crumbles beneath your touch, you step out of the subterranean darkness and into blinding, brilliant sunlight.
Quite a shock to the system, I imagine.
Oh, absolutely. The air smells intensely of rich, drying cordgrass baking in the heat. And without turning your head, your eyes perched high above your body on movable stalks scan a massive 360-degree panoramic horizon all at once.
Just taking it all in simultaneously.
You see the rippling water in the distance, the swaying green stalks of grass, and the glistening expanse of the mudflat. But then, a massive shadow sweeps over the mud.
A predator.
A great blue heron. The vibration of its landing thrums through the wet earth, traveling like an electric shock up through your legs. In a fraction of a second, you scuttle sideways with lightning speed on 8 jointed legs.
Moving incredibly fast.
You stop just short of your door, raising a massive golden brown shield into the air. And this is a weapon that weighs half as much as your entire body, and you use it to ward off a rival who has stepped just a little too close to your territory.
Wow. What an intense way to start the day.
It really is. So welcome to Saltwater Stories. I am thrilled you're here with us for today's adventure. We are traveling to the muddy, shifting edge of the ocean, where the land and the sea are in this constant daily battle.
It's a fascinating zone.
We are going to a place where one tiny, seemingly insignificant creature holds the entire coastline together. It is a story of incredible architecture, high-stakes survival, and microscopic engineering.
It truly is a life lived entirely on the edge, It's a daily high-wire act between the crushing weight of the ocean and the scorching heat of the sun.
Yeah, the extremes are just wild.
But to really understand this world, close your eyes and imagine a completely different perspective. Imagine a female wandering this exact same mudflat.
Okay, I'm picturing it.
The wind is howling across the marsh. The waves are crashing loudly in the distance, and the cordgrass is rustling frantically in the breeze.
So it's super chaotic.
Exactly. It is a chaotic, overwhelmingly noisy world. But she isn't listening with her ears. She stops walking. She feels a rhythmic, deep bass thumping traveling through the actual dirt, vibrating up through her 8 legs.
And she's feeling the ground shake.
Yeah. She pauses, feeling a weak, erratic thump to her left. She ignores it. Instead, she turns toward a strong, resonant, rhythmic drumbeat to her right. She follows this invisible music of the mud, stepping over puddles and sand, until she finds a male standing beside a perfectly round hole in the earth, waving a magnificent, brightly colored claw in the air.
That is such a vivid picture. We are stepping into the hidden, astonishing world of the fiddler crab.
We are indeed.
When you look at a mudflat at low tide, it can just look like, well, a whole lot of empty, smelly dirt.
Right, just barren mud.
But if you stand perfectly still, wait a few minutes, and just watch the ground, the mud literally begins to move. Thousands of these tiny creatures, no bigger than a plum, emerge from hidden trap doors. It becomes this bustling metropolitan city.
It is an entire hidden metropolis. And to follow that music of the mud, we first have to understand the incredible biological machinery of the creature making it.
Anatomy.
Yeah, when we look at the anatomy of a shoreline survivor like this, we are basically looking at alien blueprints. Let's start with their armor.
Okay.
A fiddler crab is encased in a hard upper shell called a carapace, made of a tough material called chitin. It acts as a physical shield against the beaks of birds or the teeth of raccoons, but more importantly, it functions as a moisture barrier.
Oh, to keep them from drying out.
Exactly. It traps water inside their bodies so their internal organs don't dry out while they're standing in the baking sun.
That makes total sense for survival, but having a rigid, hard suit of armor comes with a massive mechanical catch.
You can't grow.
Right, you cannot grow. If you are locked in a rigid box and you are constantly eating and gaining mass, you eventually run out of room. So how do they get bigger?
They have to break out of the box. It is a terrifying, highly dangerous, and mathematically precise process called molting or ecdysis.
Terrifying because they lose their armor.
Yes, exactly.
Hmm.
When the crab grows too large for its carapace, it cannot just shed it like a snake shedding its skin. The shell is really rich in calcium, which is a highly valuable
So
resource.
they want to keep it.
Right. So days before the molt, the crab's body begins to chemically reabsorb the calcium from its old shell directly into its bloodstream.
Wait, it dissolves its own shell.
Yep, it weakens the internal structure of the armor by pulling that calcium back inside itself.
So it is essentially dissolving its own house from the inside out to save the building materials for the next house.
That is a perfect way to visualize it. Once the old shell is sufficiently weakened, a seam splits open along the back.
Oh, wow.
The crab then pulls its entire, incredibly soft, jelly-like body out of the old armor. I mean, it pulls every single leg, every mouth part, even the delicate lenses of its eyes, out through this narrow opening.
That sounds less like taking off a tight coat and more like pulling your entire body out of a full body cast through a tiny crack.
While holding your breath.
Yeah. And it leaves behind a perfect ghost version of itself sitting on the mud.
And in that moment, it is completely vulnerable. It has no armor whatsoever. It has to hide deep in the darkest depths of its burrow.
It must be so stressed out.
Oh, absolutely. But here's the most fascinating part of the physical process. While it is hiding, the crab physically absorbs massive amounts of water, pumping fluid into its soft tissues to physically swell and stretch its new, soft shell up to a larger size.
Hey, it inflates itself.
Like a balloon. It holds this inflated posture for days, waiting for the newly secreted chitin to harden into a larger suit of armor.
It inflates itself like a balloon so the armor dries a size too big. That way it has room to grow into it over the next few months.
Precisely.
That is just brilliant engineering. But once they are armored up, hardened, and back on the surface, they have those eyes. We talked about them in the opening story.
The periscope eyes.
Yeah, their eyes look like tiny periscopes sitting on movable stalks on the top of their head.
What is truly breathtaking is the microscopic structure of those eyes. They don't have a single lens focusing light onto a retina like human eyes do.
So it's not like ours at all.
Not at all. They have compound eyes made up of thousands of microscopic hexagonal lenses called ommatidia.
So their vision is more like looking at a mosaic or like a digital screen made of thousands of tiny pixels.
Very similar to that. But fiddler crabs have a unique optical adaptation that you won't find in a fly or a bee.
Oh, really? What's different?
If you look closely at their eyes, you will see a dark, horizontal band that seems to track you wherever you move. This is called a pseudopupil.
A pseudopupil, like a fake pupil.
Right. Because these crabs live their entire lives on a completely flat, featureless mudflat, their eyes have evolved to be specifically adapted to view the horizon line.
That makes sense.
That horizontal band has an incredibly dense concentration of those ommatidia, giving them incredibly sharp vertical resolution right at the horizon.
So they see the horizon better than anything else.
Exactly. They possess a seamless 360-degree panoramic view of their surroundings. They can watch a bird flying behind them, a crab walking in front of them, and a shadow moving above them, all simultaneously.
Without ever turning their heads.
Never. And to add to that, they can see ultraviolet colors that are completely invisible to human eyes.
So they are scanning the horizon in high-definition 360-degree UV vision. That completely explains how they vanish down their holes a split second before a shadow even crosses over them.
They see it coming from every angle.
But here's a piece of their biology that just completely trips me up. It is a crab. It is a marine animal that breathes through gills. How on earth is a sea creature surviving for 6 hours, baking in the hot sun on dry land?
It seems impossible.
I mean, if you take a fish out of water, its gills collapse and it suffocates. Aren't these crabs just holding their breath the whole time the tide is out?
You would naturally assume they are just holding their breath, but they are actually actively breathing the air.
Actively breathing.
Yes. They possess a remarkable internal respiratory adaptation called a branchiostical lung.
Wait, they have evolved a lung? Inside a crab shell.
It functions mechanically exactly like one. Beneath that hard carapace, they have gills, just like other marine crabs, which they use to extract dissolved oxygen when they're underwater.
Okay, standard crab stuff.
But the lining of the chamber that holds these gills is highly folded, textured, and densely packed with microscopic blood vessels. When the tide goes out, the crab doesn't just empty the chamber.
It keeps water in there.
Exactly. It traps a tiny bubble of water inside.
Oh, I see where this is going. It's like a built-in scuba tank, but in reverse, they are bringing a little piece of the ocean onto the land with them.
That's a great way to think about it.
Yeah.
And they actively maintain it. As long as they keep those gills moist with that trapped water, The moisture allows the oxygen from the air to dissolve and pass into their bloodstream.
That is so clever.
If you watch a fiddler crab closely on the mud, you will sometimes see them bubbling water around their complex mouth parts.
Oh, like they're blowing bubbles.
Yeah, they are constantly cycling that stored water out of the chamber, mixing it with the fresh air outside, and drawing it back into the gill chambers to recycle the moisture and keep the respiratory system running perfectly.
So they're actively aerating their own internal water supply. That is astonishing.
It really is.
But their blood, the blood absorbing all this oxygen, it isn't like our blood, is it? If a fiddler crab gets a scrape on a sharp piece of oyster shell, it doesn't bleed red.
No, it bleeds a pale, ghostly blue.
Blue blood.
Yeah. Human blood is red because it contains hemoglobin, a protein that uses iron atoms to bind and transport oxygen. Iron turns red when it oxidizes, just like rust.
Okay, so what do crabs use?
Fiddler crabs have an open circulatory system. Instead of blood being entirely confined to neat little veins and arteries, their blood flows freely through their body cavities, physically bathing their internal organs.
Just sloshing around in there.
Pretty much.
Yeah.
And instead of hemoglobin, they rely on a protein called hemocyanin. Hemocyanin uses copper instead of iron to bind to oxygen.
Copper, and copper turns blue.
Exactly. When copper is exposed to oxygen, it turns a beautiful, vibrant blue.
Blue blood, periscope UV eyes, reverse scuba tanks. It really feels like we are describing something from another planet.
It does sound like sci-fi.
But as I was learning about their internal anatomy, I stumbled across something called coxal glands. I have to ask about these because the physical mechanics of this just blew my mind.
Ah, the coastal glands. Yeah, they are an essential part of keeping that blue blood clean. They function very much like human kidneys.
Okay, kidneys.
As the crab's cells metabolize food and create energy, they produce toxic byproducts, primarily nitrogenous waste like ammonia. If that ammonia builds up in their open circulatory system, it becomes lethal.
So they need a filter.
Right. The coxal glands filter these toxins out of the blue blood so the crab can excrete them.
Kidneys make sense. We all need a filtration system.
Yeah.
But if you think about a crab's anatomy, it's basically just a walking torso.
Yes.
Where are these kidneys located? Because they are in the lower back.
No, they are located directly in the crab's head.
The kidneys are in its face.
Yes, they are. They are situated right near the base of the eyes.
Great.
And the waste fluid that these glands filter out is excreted through tiny microscopic pores located near the base of their antenna.
So mechanically speaking, if the kidneys are in the face and the exhaust ports are near the antenna, they are essentially peeing out of their faces.
From a purely functional standpoint, yes. They excrete liquid waste from their faces.
Yeah. I love how nature solves a problem based purely on what space is available. Like, sure, put the kidneys in the head, why not?
It works for them.
But wait, we haven't even talked about the stomach teeth. I promise, we are not making this up.
We absolutely are not making this up. Fiddler crabs do not have teeth in their mouths. Their mouth parts are designed for sorting and sifting, not chewing.
So they just swallow their food whole.
Relatively whole, yes. So to break it down, they have evolved a complex mechanical structure inside their stomachs called a gastric mill.
A gastric mill. That sounds industrial.
It acts like it. This is an arrangement of hard, calcified, tooth-like plates that sit inside the stomach lining. Rhythmic muscle contractions cause these plates to grind against each other, physically crushing the food, breaking open plant cells, and sorting the nutrition from the indigestible sand.
So they literally chew their food after they swallow it.
Yes, and this internal machinery leads to a completely unexpected defense mechanism.
A defense mechanism using stomach teeth.
Biologists recently discovered that when a fiddler crab is cornered in his burrow, say a raccoon is digging at the entrance or a larger crab is trying to invade, it can intentionally grind those internal stomach plates together vigorously.
Wait, it growls from the inside.
It is a process called stridulation. By rubbing those calcified plates together, the friction creates a loud, rasping acoustic warning that echoes up through the mud.
Wow.
The crab generates an intimidating growl from deep inside its gut without ever having to open its mouth or lift a claw.
A growling stomach as a literal weapon of intimidation. I think that felt that way when I'm really hungry, but this is next level.
It's extremely effective.
But as amazing as all this internal prumbing is, the internal teeth, the face kidneys, the blue blood, they are spending an enormous amount of calories maintaining it.
Oh, a massive amount.
And where is all that energy going? Because they aren't swimming across the ocean. They are sinking all of that energy into the main event.
The defining feature.
Exactly, the giant claw.
This is what makes a fiddler crab a fiddler crab. It is one of the animal kingdom's most extreme examples of sexual dimorphism, where males and females of the exact same species look dramatically different.
Right, the females look totally different.
Female fiddler crabs are wonderfully symmetrical. They have two small, equal-sized claws that are perfectly designed for picking up food. Males, however, have one small feeding claw and one absolutely massive major claw.
And when we say massive, we really have to scale this up to understand the physical burden.
We do.
That single major claw can weigh up to 50% of the crab's total body mass.
Half of their entire weight.
Think about the physics of that for a second. If you are a human being, imagine having one single arm that weighs as much as your head, your torso, your other arm, and both of your legs combined.
It's hard to even picture standing up.
Imagine the sheer muscular effort required just to stand upright without tipping over, let alone hauling that massive weight across a sticky mudflat all day just to wave it at people.
It is the most metabolically expensive structure the crab possesses. The biological cost is staggering.
It must be.
It requires massive amounts of energy to grow the chitin, dense muscle fibers to operate it, and immense stamina to wave it for hours on end in the sweltering heat.
So from an evolutionary perspective, why build it? If it is such a burden, what is the payoff for lugging around a 50-pound arm?
It serves three primary vital functions for the male. First, it is a formidable weapon.
Okay, weapons make sense.
Mudflats are crowded, and prime real estate, like a burrow in the perfect spot where the mud is just right, is highly contested. When two males want the same territory or are competing for the attention of a female, they will face off.
A crab fight.
They interlock those giant claws and engage in a highly ritualized, incredibly tense wrestling match. It is a test of sheer torque and leverage, pushing and twisting each other.
Do they hurt each other?
Usually the weaker male will realize he is outmatched and back down before anyone gets a cracked shell.
That's good. And the second function?
Second, it is a billboard. They wave it in specific, rhythmic patterns to attract females, proving their vitality. We will get into the intricate nuances of that wave shortly.
And the third function, because I know this was a relatively recent discovery, and it changes how we view the claw entirely.
It really does. For a long time, observers simply assumed the claw was a terrible burden outside of mating and fighting. But when they looked at the crabs through thermal imaging cameras, the heat signatures revealed something spectacular.
What did they see?
The giant claw acts as a desert cooler, a thermodynamic heat sink.
Like the middle fins on a computer processor, or the radiator on a car.
Exactly like that. When the crab is standing out on the dark, baking mudflat, its dark shell absorbs a massive amount of solar radiation.
They must get so hot.
They do. But the giant claw has an enormous surface area. Blood circulates from the crab's hot core out into the vast network of vessels inside the giant claw.
And then what happens?
As the coastal breeze blows across the large surface area of the claw, it dissipates the heat through convection, drawing the heat out into the air.
Wow.
Intact males actually stay significantly cooler in the sun than crabs that have lost their major claws. This cooling effect offsets the immense energy cost of carrying the claw, allowing the male to spend more time up on the hot surface feeding and waving, while other crabs are forced to retreat underground to cool off.
So it's not just a weapon, it's a built-in air conditioning unit.
Pretty much.
But you just mentioned losing a claw. What happens if a heron swoops down and grabs the crab by the claw, or a wrestling match goes terribly wrong? I mean, if that claw is half your body weight and your main defense and it gets ripped off, aren't you doomed?
You'd think so. But the crab has evolved a brilliant emergency protocol. In fact, if a bird grabs a crab by the leg or the claw, the crab can voluntarily sever its own limb biological process called autotomy.
They just pop it off.
They have specific fracture planes built into their joints.
Mm.
With a sharp muscle contraction, they snap the limb off, seal the wound instantly to prevent blue blood from leaking, and drop to the mud to escape while the bird is left holding an empty claw.
That's intense. But they're still missing their main weapon.
They were not doomed, though, because over the next few molting cycles, the male will miraculously regenerate a brand new major claw on that exact same side.
Wait, let me clear something up right here. I always heard a story, like a kind of beach myth, that if a fiddler crab loses the big claw, its body compensates by turning the remaining small feeding claw into the new giant claw, and a new small claw grows on the empty side. Like they completely switch handedness to save time.
That is a very common beach myth, and it is largely because people confuse them with snapping shrimp, which actually do switch sides when they regenerate.
Oh, interesting.
But fiddler crabs are genetically hardwired to be either right-handed or left-handed from the moment they are born. The new giant claw grows exactly where the old one was.
Okay, myth busted. But there is a fascinating deceptive twist to the physical makeup of this newly regenerated claw, isn't there?
And this is where the story gets really wild. The new claw looks identical, but it isn't exactly the same.
It's far from it.
Generating that much dense, crushing muscle mass takes an enormous amount of time and caloric energy the crab might not have while trying to survive. So the crab takes a biological shortcut. It grows what is called a leptoculous claw.
A leptoculous claw. What does that mean physically?
The new shell grows to the exact same length, shape, and bright color as the original claw, but inside it is essentially a hollow prop.
It's hollow.
It lacks the heavy muscle mass, the density, and the crushing torque of the original claw.
It's a decoy.
It is a profound biological bluff. In behavioral ecology, we call this dishonest signaling. From a distance, to a rival male scanning the beach, or an observing female judging potential mates, the crab looks just as massive, just as powerful, and just as dangerous as he did before the injury.
So he is walking around the beach with a giant hollow foam finger, pretending he can still bench press 200 pounds.
Yes.
He's relying entirely on his past reputation.
And the incredible thing is, the bluff actually works. It rewires the social dynamic of the beach.
Because no one wants to find out if it's real or fake.
Exactly. Because the cost of getting into a physical fight with a genuinely strong male is so high you could lose your own claw or get crushed. Rival males will often take one look at that massive, freshly regenerated leptoculous claw and retreat without ever testing its actual strength.
So the fake claw buys him time.
The bluff buys the injured crab time, safety, territory, and mating opportunities he wouldn't otherwise have any right to claim.
It is the ultimate fake it till you make it strategy.
Truly.
But do the females fall for it? Are the females just looking at the sheer size of the claw, or are they evaluating something deeper and more specific?
This is a question that deeply fascinated observers. To test how discerning and analytical female fiddler crabs really are, biologists had to remove all the other variables like the color of the crab, the size of its body, or the smell of its burrow.
How do you do that?
They needed perfect mathematically controlled males, so they built robotic crabs.
Building mechanical crabs to trick real crabs. The lengths we go to for understanding.
It is incredible ingenuity. They built tiny mechanical crabs with interchangeable 3D printed claws.
That's amazing.
These robots could be programmed by computers to wave at very specific, mathematically precise speeds and rhythms. They took these mechanical imposters out onto the actual mudflats, placed them near real crab burrows, turned them on, and watched how the living female fiddler crabs responded to the robotic waves.
So what did the females do? Did they see through the matrix?
They proved that they are intensely, ruthlessly discerning. The females consistently gravitated toward the robots that has larger claws, and they strongly preferred robots that wave those claws at faster speeds.
Okay, so bigger and faster is better.
Yes. When they presented a female with two robots waving at the exact same speed, she chose the one with the bigger claw. But when they presented her with two robots sporting the exact same size claw, she always chose the one waving faster.
Because waving a giant, heavy object in the air rapidly requires incredible stamina and peak cardiovascular health. You cannot fake the metabolic energy required to do that, even if you are holding a hollow foam finger.
You've hit the nail on the head. The visual display is an honest, unforgeable indicator of physical fitness and genetic quality. The female knows that a male who can wave a giant claw that fast, in the baking heat, without collapsing, has a spectacular respiratory system and strong genes to pass on to her offspring.
Okay, but hauling that claw around, using it as an air conditioner, and waving it fast enough to impress a highly critical female, that burns a massive amount of calories.
A huge amount.
Which leads us to a huge physical problem. If half of your body is a giant weapon that you absolutely cannot use to pick up food, how does a male crab actually eat enough to survive?
This is the extreme trade-off of that massive armor. Let's look at the females first.
Right, they have two small claws.
Female fiddler crabs use both of their small claws to eat. They alternate hands, scooping mud to their mouths in a rapid, highly efficient two-handed buffet.
Just going to town on the mud.
The male, however, is forced to feed exclusively with his one single small feeding claw.
He has to eat every meal of his life with one hand tied behind his back.
Quite literally.
Yeah.
Because of this feeding inequality, males are inherently disadvantaged. They have to work twice as fast as the females and spend significantly more time up on the dangerous surface foraging just to extract the exact same amount of daily nutrition.
So let's talk about the mechanics of that meal. What exactly is on the mudflat menu?
Good question.
When you watch them, they're just scooping up wet dirt and pushing it against their mouths. Are they literally eating the mud?
They are what we call deposit feeders. They are not actually eating the physical grains of sand or silt. They are after the invisible film of life coating the surface of that sediment.
Invisible life? Like what?
A single teaspoon of that wet mud contains hundreds of millions of microscopic organisms. They are eating detritus, which is the decaying organic matter of marsh grass, along with single-celled algae, golden green microscopic plants called diatoms, and incredibly rich, energy-dense colonies of bacteria.
So they scoop up a pinch of wet mud, bring it up to their face, and then what is the physical mechanism? How do you get invisible bacteria off a grain of sand?
This is where their complex mouthparts perform microscopic magic.
Yeah.
Inside their mouth, they don't have a tongue. They have highly specialized appendages covered in stiff, microscopic, brush-like hairs called setae.
Like little brooms.
And the physical shape of these hairs is perfectly evolutionarily adapted to the specific texture of the environment the crab lives in.
So different crabs have different tools depending on the dirt.
Exactly. Take the Atlantic sand fiddler crab, for example, which lives on hard, coarse, sandy beaches. Their mouthparts are packed with setae that are shaped like tiny microscopic spoons.
Little spoons.
These stiff little spoons act like rigid scrub brushes. When the crab puts a grain of sand in its mouth, the spoons violently scrape the algae and bacteria off the hard, inorganic surface of the sand.
Wow.
But if you look at a marsh fiddler crab, which lives in deep, gooey, silty mud where the particles are incredibly fine, spoon tips wouldn't work. The mud would just clog them up.
Oh, sure, it would turn into paste.
Instead, they have plumose setae microscopic hairs, shaped like delicate, highly branched feathers. These feathers are perfectly designed to filter and sieve the soft, liquid silt, trapping the bacteria while letting the water flow through.
That is specialized microscopic engineering. Okay, so they scrub the sand grain with their spoon hairs, swallow the invisible bacteria and algae into their gastric mill, and then what happens to the clean grain of sand left in their mouth?
They spit it back out, but they don't just drop it haphazardly.
No.
After the organic material is thoroughly extracted, the crab uses its mouthparts to compact the clean inorganic sand into a perfect, dense little sphere and then gracefully drops it on the ground beside them. This is called a pseudofecal pellet.
Pseudofeces. Fake poop.
Precisely. It hasn't passed through their digestive tract at all. It is just the rejected, scrubbed, clean sand from their mouth.
I've seen these.
Have you? If you ever walk on a beach or a mudflat at low tide and see thousands of tiny, perfectly round little balls of sand radiating out in intricate patterns from a crab hole, those aren't eggs, and they aren't waste. They are the leftovers of a fiddler crab's breakfast.
Just tiny discarded sand balls.
By doing this constantly, millions of times a day, they are essentially acting as the microscopic cleaning crew of the coastline, churning the soil and recycling dead organic material back into the living food web.
But wait, if they're just indiscriminately scooping up whatever's on the surface of the mud, tossing it into their mouths, separating it with feather hairs, and swallowing the tiny bits, do they ever accidentally eat things that aren't food?
Like what?
Because human pollution is everywhere in these coastal zones.
This brings us to a deeply concerning but mechanically astonishing reality.
Yes, they do.
They eat our trash. Our coastlines, especially tangled environments like salt marshes and mangrove forests, act like giant nets, trapping enormous amounts of human plastic waste. Over time, sunlight, salt, and the mechanical pounding of the waves slowly break plastic bags and bottles down into tiny fragments called microplastics.
And those just sit on the mud.
These fragments eventually sink and settle right into the top layer of the mud.
Right in the exact zone where the fiddler crab is deposit feeding.
Right in their feeding zone. And when the crabs rapidly scoop up the mud, their setae cannot always distinguish between a piece of hard algae and a tiny fragment of plastic, so they accidentally ingest these microplastics.
Oh, that's...
But remember the gastric mill? Those hard, calcified stomach teeth we talked about earlier?
Oh no, you're telling me they are chewing up the plastic inside their stomachs.
Mechanically, yes. As the microplastics pass through the intense grinding action of the gastric mill, the crabs physically shred and pulverize the plastic fragments into even smaller, microscopic particles called nanoplastics before finally excreting them back out into the environment.
So the crab is unintentionally acting like a tiny biological plastic shredder.
Observers studying this phenomenon in the Caribbean found that the sheer mechanical force of the fiddler crab's stomachs is accelerating the physical breakdown of plastic on a timeline of mere days, rather than the centuries it would normally take a plastic bottle sitting in the sun.
On the surface, that sounds like a miraculous cleanup crew. They are breaking down our mess faster than nature normally could.
It certainly highlights the incredible mechanical resilience of their digestive systems, but structurally, it creates a massive problem for the food web.
Why is that a problem?
When a piece of plastic is shredded from a microplastic down into a nanoplastic, it becomes incredibly dangerous. Nanoplastics are so infinitesimally small that they can cross cellular barriers. They can pass through intestinal walls and enter bloodstreams.
Oh,
Because the crabs make the plastic smaller, it becomes much easier for microscopic organisms, like plankton, filter-feeding oysters, and tiny fish, to accidentally absorb them. The crabs are inadvertently pushing these synthetic materials much deeper into the foundational base of the ocean food web.
so by simply trying to eat their breakfast, their internal anatomy is physically changing the structure of the pollution around them. That is a heavy reality to digest.
It really is.
But when they aren't eating or engaging their gastric mills, they are talking. And I want to go back to the music of the mud. We established that they do not have voices.
They have no vocal cords whatsoever. Their complex society relies entirely on a hidden language of motion, vibration, and rhythm.
The waving.
We talked briefly about the visual waving, but the mechanics of it are incredibly intricate. Every single species of fiddler crab has its own distinct waving dialect.
Wait, they wave differently depending on the species.
Oh yes. Some species lift the claw and wave it in slow, graceful, sweeping circular motions. Others thrust the claw straight out and jerk it up and down in rapid staccato pumps.
So a female wandering the mudflat knows exactly which species is waving at her just by recognizing the specific rhythm and geometry of the wave.
Yes, but the males aren't just waving at the females. They're actively using this waving to eavesdrop on each other.
Eavesdropping visually, how does that work?
It is all about conserving energy. Imagine a male crab standing by his burrow. He is waving at a relaxed, steady, low-energy pace. Suddenly, the male 3 feet away from him starts waving frantically, pumping his giant claw as fast as his muscles can manage.
Something's got him excited.
The first male sees this change in rhythm out of the corner of his panoramic eye, and he immediately speeds up his own wave rate to match. He hasn't even seen a female yet,
He's just copying the neighbor.
but he knows that his neighbor wouldn't be wasting that massive amount of precious metabolic energy unless a female is walking nearby. He uses the neighbor's visual display as a social cue to step up his own game.
That is incredibly smart. Let the other guy burn the calories doing the lookout work and just match his energy when it counts.
Very efficient.
But you mentioned in the opening story that the marsh is a chaotic, noisy place.
Yeah.
The wind is blowing the cordgrass, the water is moving. If a female is far away, or there is a ridge of mud or tall grass blocking her line of sight, how does she even see this frantic waving?
She doesn't always have to see it.
Huh.
And this is where we return to the drumming.
Right, the music.
When a male senses a female approaching, he doesn't just rely on the visual billboard. He performs a multimodal serenade. Let's look at the mechanical sequence of the West African fiddler crab Africa tangeri.
This is one of the biggest fiddler crabs, right? The one with the spectacular bright purple, yellow, and orange claws.
Yes, their colors are stunning. When a female approaches, the male begins step 1, a slow arcing visual wave.
Yeah.
The visual billboard.
Step 1.
If she's interested and steps closer, he moves to step 2. He drops his heavy carapace down against the wet mud, rocking his body while he continues to wave.
Getting lower to the ground.
Step 3. He begins drumming the heavy base of his giant claw directly onto the ground, creating rhythmic, seismic thumps that travel through the soil.
He is physically beating the ground like a drum.
And step 4. If she is very close, but still hasn't committed, he runs halfway down into the mouth of his burrow and begins drumming against the inside wall of the tunnel, turning the hole itself into an acoustic amplifier, sending vibrations deep into the earth.
But how does the female actually process this information? You said earlier that they don't have ears.
They don't have ears on their heads. They listen with their knees.
Wait, what? They listen with their knees.
Yes, they do.
So they are picking up sound waves through their joints.
Exactly. Located in the joints of their walking legs is a highly specialized microscopic sensory structure called Barth's myochordatonal organ.
Let's break that down. Barth's myochordatonal organ. How does a leg joint act as an ear?
Think of it as a biological seismograph. Spiders have a very similar structural organ in their legs to feel the delicate vibration of a fly struggling in their web.
Oh, I've heard of that.
The fiddler crab uses this organ to detect the seismic thumping traveling through the moisture in the wet dirt.
Through the actual mud.
The sound waves physically travel through the mud, hit the crab's feet, and travel up the exoskeleton to vibrate the membrane in the joint. She translates those physical vibrations into acoustic information. She is quite literally hearing his song through the soles of her feet.
So she can physically feel the bass drop in the music of the mud.
She feels the bass, the rhythm, and the intensity. And this isn't just a random beat to get her attention.
There's a message in it.
Observers placed highly sensitive underground microphones called geophones to record these hidden love songs. By analyzing the acoustic data, they discovered that the vibrations tell a highly specific story.
What's the story?
Larger males with heavier bodies, denser muscle mass, and heavier claws create louder, much lower frequency thumps when they hit the ground.
The physics of mass. A heavier object striking the ground naturally creates a deeper resonance, so it is another honest signal.
You got it.
You cannot fake a deep bass thump if you are a tiny, lightweight crab, or if you are carrying around one of those hollow, fake, liptochless claws. The ground won't shake the same way.
The acoustic vibrations are physically, unalterably tied to the true mass of the crab. He cannot lie about his strength in the dark. The female uses this seismic Morse code of the mud to evaluate the exact physical fitness and true weight of a partner before she even lays eyes on him.
So they're drumming on the ground, creating these complex vibrations to find a mate. But this drumming, and more importantly, the actual tunnels they are digging to drum inside of, that architecture physically changes the planet, doesn't it?
It does. If we zoom out and connect this microscopic behavior to the bigger ecological picture, fiddler crabs are what we call ecosystem engineers.
Like earthworms churning up the soil in a garden, or a beaver damming a river and creating an entirely new wetland. By just living their lives, they physically alter the landscape for everything else.
That is the perfect comparison.
Yeah.
To understand how vital their engineering is, you have to understand the chemistry of the mud they live in.
Okay, set the scene.
If you take a shovel and dig just a few inches down into a coastal salt marsh, the mud changes. It turns pitch black, and it smells strongly of rotten eggs.
I know that smell perfectly. If you've ever stepped in marsh mud, it releases that sulfuric scent. It is the signature smell of the coast.
That distinct smell is hydrogen sulfide gas. The mud down beneath the surface is highly anoxic, meaning it is completely devoid of oxygen.
No oxygen at all.
Because the water blocks the air, anaerobic bacteria take over, and toxic chemicals build up in the soil. In that harsh, suffocating environment, the roots of the marsh plants struggle to breathe.
So the grass is basically choking down there.
Enter the fiddler crab. Using their small walking legs, they tirelessly excavate deep J-shaped tunnels, sometimes reaching 2 feet beneath the surface.
2 feet deep. That is a massive excavation project for a crab the size of a coin. It's like a human digging a well by hand.
It really is. They haul all of that deep, black, anoxic mud up to the surface one tiny scoop at a time, and in doing so, they create millions of open pipes leading down into the earth.
And that lets the air in.
This physical mixing of the soil is called bioturbation. As the tide recedes, fresh oxygen from the air flows down into these burrows, penetrating deep into the soil and aerating the mud.
So the crab colony is essentially acting like a giant mechanical lung for the entire marsh ecosystem.
They are the lungs of the coast, and this oxygenation is critical for the survival of Spartina cordgrass, the foundational salt marsh plant whose dense root systems physically lock the mud together and stop the coastline from washing away in a storm.
So the crabs keep the grass alive, and the grass keeps the coast from washing away.
Exactly. The crabs aerate up to 35% of the sediment, giving the roots the oxygen they desperately need to grow deep and strong. Furthermore, when scientists examined the microbiome of these crabs, they discovered that microscopic bacteria living directly on the hard shells of the fiddler crabs pull nitrogen gas out of the air and convert it into a nutrient-rich form.
Wait, the crab itself is acting as a mobile fertilizer factory.
Yes. As they scuttle around and brush against the soil, they are turning over the earth, piping oxygen to the roots, and physically fertilizing the plants with every step they take.
It is breathtaking how much foundational architecture is happening right under our feet. And you mentioned earlier that some of these burrows aren't just holes in the ground. Some crabs are actually building structures above the ground.
The architectural diversity among different species is stunning. Take Zaruca formosensis, the Taiwanese fiddler crab. The males of this species don't just dig a hole. They painstakingly gather wet mud and build tall, cylindrical chimneys rising up into the air, completely circling their burrow entrances.
Like little mud smokestacks dotting the beach. Why do they expend the energy to build a tower?
The physics of the chimney serve multiple ingenious functions. On a massive, flat, featureless mudflat, a tall tower acts as a visual landmark. If a bird attacks and the crab has to scatter, that chimney helps the male instantly locate his exact hole in a panic.
Ah, a homing beacon.
More importantly, it harnesses wind currents. By raising the opening of the burrow higher into the coastal breeze, it creates an aerodynamic pressure differential that helps draw cool air up from the damp earth below, physically regulating the temperature inside the deep tunnel during the hottest parts of the day.
So if these crabs are this beneficial to the environment, aerating the soil, fertilizing the roots, building thermal chimneys, they must be the absolute heroes of the ecosystem everywhere they go, right?
This brings us to an incredibly important and quite tragic lesson about the delicate, intricate balance of nature. When the environment changes too quickly, even the heroes can become inadvertently destructive.
Really? How so?
Let me tell you the story of the Atlantic marsh fiddler crab, Manuka pugnax.
Okay, I'm listening.
For centuries, this particular species lived happily along the eastern coast of the United States, but their habitat had a strict northern border. They stopped at Cape Cod, Massachusetts.
Why did they stop there?
The waters of the Gulf of Maine, just north of Cape Cod, were simply too cold for their delicate microscopic larvae to survive. Cape Cod acted as a natural thermal brick wall.
But the global oceans are warming.
Rapidly. The Gulf of Maine is currently warming faster than almost any other ocean basin on the planet. Driven by this influx of warm water, the thermal wall collapsed. The fiddler crabs suddenly became climate migrants.
Wow, they moved north.
In 2014, an observer walking through a salt marsh north of Cape Cod spotted a fiddler crab scuttling through the grass. It was a shocking, unprecedented discovery. Since that moment, driven by the warming waters, they have marched steadily north, moving past New Hampshire and pushing deep into central Maine.
On the surface, that sounds like a massive success story. They survived a changing climate by adapting and moving. They found a new home, and now they get to keep aerating the soil and helping the grass grow up in Maine.
That is exactly what you would assume based on their history. But remember the physics of the ecosystem. The salt marshes in Maine evolved over thousands of years without the presence of burrowing crabs.
Oh no, I see where this is going.
The Spartina grass in the north never needed to develop the deep, thick, robust root systems that the southern grass uses to tolerate having the soil constantly churned up.
Because I never had to deal with the digging.
When these new southern crabs arrive in Maine and enthusiastically start digging their massive J-shaped tunnels, their sharp legs and constant excavation are physically severing the delicate, shallow roots of the northern grass.
They're destroying the grass by trying to help it.
In these newly migrated territories, the grass isn't thriving, it is collapsing. The northern marshes are suffering up to a 40% loss of above-ground plant mass because the roots are being destroyed from below.
So a biological behavior that is completely beneficial, vital, and life-sustaining in New York or Virginia becomes actively destructive in Maine, purely because the local plants haven't had thousands of years to adapt to the digging.
That is the core of the tragedy. It shows us that climate change doesn't just make things warmer. It forces species into novel, untested interactions that can rapidly destabilize foundational ecosystems.
They're just doing what they've always done.
The crabs aren't doing anything malicious or wrong. They're just doing what their DNA has told them to do for millions of years. But the context of the world around them has shifted.
It is a powerful reminder that you cannot just pick up a puzzle piece from one box and expect it to fit perfectly into another puzzle.
That's a great way to put it.
But this raises a massive logistical question. To understand how a crab the size of a plum could migrate hundreds of miles up the coast to Maine in the first place, we have to look at how they travel. They aren't walking hundreds of miles on those little legs. How did they cross the ocean?
To understand that grand journey, we have to look at the miraculous and frankly terrifying first weeks of a fiddler crab's life. And the entire journey begins with precise timekeeping.
Timekeeping, you mean tracking the tides?
Yes, but the physical mechanics of it are profound. Fiddler crabs don't wear watches, and they can't see the moon from inside a dark mud burrow. But their cells possess two distinct internal biological clocks running simultaneously. First, they have a 24-hour circadian clock tied to the rotation of the Earth and the Sun, which regulates their daily color changes.
Color changes. They change color.
Yes, their shell contains pigment cells called chromatophores. They use this 24-hour clock to turn darker during the day to protect their internal organs from UV radiation, and then turn paler at night when the sun goes down.
That's amazing.
But alongside that, they have a separate 12.4-hour circumtidal clock tied entirely to the gravitational pull of the moon and the shifting of the tides.
So they internally biologically know when the tide is changing, even if they can't see or feel the water.
Exactly. If you take a fiddler crab from the beach and put it in a dark, temperature-controlled, silent laboratory tank hundreds of miles away from the ocean, it will still become active, pace around the tank, and look for food at the exact moment it would be low tide back on its home beach. Its cells carry the rhythm of the ocean inside them.
That is hauntingly beautiful. They carry the physical memory of the ocean's gravity. And how do they handle the changing seasons, especially those new migrants facing the freezing winters up in Maine?
When the temperatures begin to drop, they use those internal clocks to know it is time to shut the system down. They dig deep below the frost line, seal their burrows tightly, and enter a physiological state of torpor, a deep hibernation where their heart rate and metabolism slow to an absolute crawl.
It's just waiting out the cold.
They become the crustacean equivalent of a dormant seed surviving the ice, just waiting for the spring thaw.
So they wake up in the spring, they use the clocks to track the tides, and they use these clocks to know the precise mathematical moment to release their babies, right?
Yes, the timing is a matter of life and death. When a female is carrying thousands of fertilized eggs tucked tightly under her abdomen, she waits in the safety of her burrow. She is waiting for a very specific astronomical event, the spring tide.
The spring tide, that is the highest, most powerful tide of the month, aligning with the new or full moon when the gravitational pull is strongest.
Precisely. Under the cover of darkness, on the exact night of the highest tide, she walks to the edge of the rushing water and releases her eggs. The moment they hit the salt water, they hatch instantly into microscopic, alien-looking larvae called zoa.
They don't look anything like crabs at this point, do they? I've seen pictures. They're just tiny, translucent, floating specks with massive eyes and a long, sharp spike sticking out of their back to stop small fish from swallowing them whole.
They are completely planktonic, and this is where the incredible perilous migration happens. The zoea are far too small to swim against the massive physical power of the ocean currents, but they absolutely do not want to stay in the marsh.
Why not? The marsh seems safe.
The coastal marsh is packed with small fish, oysters, and filter feeders that would eat them instantly. They need to get out to the open ocean to hide in the vastness of the water column.
So if they are the size of a grain of sand and they cannot swim against the current, how do they get out to the ocean?
They use a brilliant behavioral strategy called selective tidal stream transport, or STST.
Let's unpack the physics of STST. How does a microscopic speck outsmart the massive flow of the ocean?
They use that internal circumtidal clock we talked about.
Yep.
When the tide begins to roll out toward the ocean, the tiny larvae actively swim up toward the surface of the water. The surface water moves the fastest, so they catch this outgoing current, riding it like a high-speed express bus heading out of the estuary.
Catching the express current out to sea. But eventually the tide turns around and pushes back in.
Exactly. And when their internal clock tells them the tide is turning and starting to rush back into the marsh, the larvae immediately stop swimming. They sink straight down to the bottom, hiding in what is called the boundary layer.
The boundary layer.
Because of the friction against the mud, the water right near the bottom moves much slower. They hide in this slow water so they aren't pushed all the way back to where they started. They wait out the incoming tide in the dark, and when the tide rolls out again, they swim back up to the surface and catch the next bus.
They are actively, consciously riding the tides out to sea. They are playing the currents. That is staggering navigational intelligence for a creature that doesn't even have a brain fully formed yet.
It's pure survival instinct mapped to the moon.
So they ride this bus for weeks out in the terrifying open ocean, avoiding whales, jellyfish, and fish floating for hundreds of miles, which perfectly explains how they migrated all the way up the coast to Maine.
That is exactly how they travel. The ocean currents act as a global, high-speed conveyor belt. Out in the safety of the open ocean, they feed, they molt, and they transform into their next stage called a megalopa.
A megalopa, what's that look like?
They start to look a little bit more like a tiny crab, developing miniature claws and a swimming tail. But eventually their biological imperative kicks in. They have to come home. They cannot survive in the open ocean forever. They need mud to build a burrow.
But how do you find your way back to a mudflat? The ocean is infinitely huge. How does a speck of a crab find a specific patch of smelly mud from miles offshore?
They follow their nose. The megalopa larvae drift on the currents until they eventually cross into shallower coastal waters. Then they begin actively smelling the water, searching for a highly specific chemical signature humic acid.
Humic acid, what makes that smell?
Humic acid is the chemical compound released by decaying marsh grass, wet soil, and the presence of adult fiddler crabs. It is the signature, unmistakable scent of a healthy, functioning mudflat.
Oh, the smell of home.
When the megalopus smells that chemical in the water, it knows it is close to home. So it simply reverses its tidal transport strategy.
She changes direction.
Now it drops down to the bottom during the outgoing tides to hold its ground, and it swims up to the surface during the incoming tides, riding the current back into the estuary.
Following the scent trail home, riding the tide like an elevator?
Once they find the perfect mudflat, they settle down to the bottom, shed their swimming tail, and undergo one final, miraculous metamorphosis. They transform into a miniature, fully formed fiddler crab, ready to dig its very first J-shaped burrow and begin its life on the edge of the land.
It is an absolute epic odyssey from start to finish, and tracing that journey brings us completely full circle. Let's go back to that opening scene we started with. We are standing on the edge of the mudflat again. The tide has retreated, the mud plug pops open, and the fiddler crab steps out into the blinding sunlight.
But now, when we look at the mud, we don't just see a bug scuttling in the dirt. We understand exactly what it is doing and the miraculous machinery driving it.
We see that massive golden brown claw, and we know it isn't just a heavy burden. It is a thermodynamic heat sink, keeping the crab's blue blood cool in the baking sun, and an honest billboard broadcasting its physical stamina.
We see it scooping up the mud with its small claw, and we know those microscopic feather-like bristles are perfectly sorting invisible bacteria from sand before it drops a clean pseudo-fecal pellet back onto the beach.
And when a shadow passes over and the crab dives into its burrow, we know that tunnel is pulling a breath of fresh, life-giving oxygen deep down into the toxic and noxic earth, allowing the roots of the marsh grass to breathe, thrive, and hold the very coastline together against the crash of the waves.
And when the marsh is noisy, we know to look closer. To see the male dropping his carapace against the mud, thumping out a deep bass rhythm, a seismic Morse code of survival and mass, while a female stands yards away, listening to his song through the joints in her knees.
It is a vibrant, deeply interconnected world happening right beneath our boots, governed by the rhythm of the moon.
It truly is.
And taking this journey leaves me with one final lingering thought. So often we look at nature and we value things based on their sheer physical size. We marvel at the breaching whale or the towering redwood tree or the apex predator pacing the plains. But ecological power doesn't depend on physical size.
Not at all.
If a creature the size of a plum can carry the precise gravitational rhythm of the moon in its tiny cells and physically alter the geology of the coastline with its footsteps, it makes you wonder, what invisible rhythms are we carrying inside our own biology? Beneath our digital distractions and our modern schedules, do we have deep tidal or celestial clocks running in our own cells that we haven't even discovered yet?
The natural world always holds a mirror up to us if we were willing to look closely enough.
Without this tiny creature relentlessly rolling little sandballs, filtering out microplastics, and digging millions of tiny tunnels, the vibrant coastal worlds that protect our cities from storms would simply suffocate and cease to exist. Every single footprint in the mud matters. Thank you so much for joining us on this adventure to the tidal edge. We hope you never look at a muddy shoreline the exact same way again. Until our next adventure, keep exploring, and we'll see you next time on Saltwater Stories.